Hello students. In this video, I am going to calculate the eigenvalues for angular momentum operator L square and Lz, and we are going to use the ladder operator techniques without actually knowing the functional form of eigenstate. So let us proceed. So in the last video, we have derived some important commutation relation, and we told that L square Lz, they both commute to each other, and when two operator commutes with each other, they have a simultaneous eigenbasis. So that means they have simultaneous same eigenstates. So I write the eigenstate by alpha beta, and when L square operates on this one, you get the eigenvalue alpha, and when Lz operates on this one, you get the eigenvalue beta, alpha beta. Now here I will use the two indices for defining the state. Like in the case of harmonic oscillator, you only define the state by n, but here because we have two operators, both have a same eigenstate, but their eigenvalues are different. So I am denoting the state by two indices alpha and beta. Now let us say I say if alpha beta is the state for eigenstate for Lz, if I calculate L plus over alpha beta, so I claim that this is also a eigenstate for Lz. So let us calculate now what happens when Lz operates on L plus alpha beta. So now we have seen in my last class where we shown that Lz and L plus do not commute to each other. When I take Lz, L plus minus, I got plus minus H cross L plus minus. So here I have Lz L plus. Okay, so Lz L plus is equal to plus H cat L plus. That means these two operate, do not commute. Now I cannot operate L plus on alpha beta because for the time being I don't know how alpha plus will operate on alpha beta, but I know how Lz operates on alpha beta by this equation. So instead of writing Lz L plus, I write now L plus Lz using this equation. This equation says, this commutator says Lz L plus minus L plus Lz is equal to plus H cut L plus. So I want now Lz L plus, so this will be equal to L plus Lz plus H cut L plus. Now this I will operate on state alpha beta, and when I operate this on alpha beta, what will happen? Lz operates on alpha beta, you beta here, so this become beta L plus, this become beta L plus, and this H cut L plus H plus S plus, and this is you have same state alpha beta, and now I can write this as a beta plus H cut is equal to L plus alpha beta. That means this state is a eigenstate of Lz with eigenvalue beta plus H cut. That means the operation of L plus on alpha beta increases the eigenvalue of Lz by H cut. Okay. Similarly, I can show that if I instead of L plus, now suppose if I operate, say, I operate Lz on L plus square alpha beta, then what will happen? Then let us calculate now. So for that I require the commutation relation of Lz plus alpha square. I want to operate this one. So L plus I cannot operate here, so I need commutation relation Lz L plus square. So Lz L plus square will be Lz L plus L plus plus L plus LZ L plus. I'm writing it as L plus L plus. Now LZ plus L plus, we know already this is what this is plus H cut L plus square L plus. Similarly here again this become H cut L plus L plus. So now this become plus 2H cut plus 2H cut L plus square. Okay, now let us operate this on here. So if I operate here, say when I operate my LZ on L plus square alpha beta, okay, so I can write LZ L plus square equal to, I'm writing L plus square LZ because it's a commutation. So L plus LZ plus 2H cut plus 2H cut L plus square, and now this has to operate on the state alpha beta. So when I operate this one, what will happen? LZ operates, beta will come, and so this becomes beta plus 2H cut L plus square alpha beta. So that means L plus square alpha beta is again eigenstate of LZ with eigenvalue beta plus 2H cut. So if I apply L3, this will be beta plus 3H cut. If I apply L4, it will be beta plus H4. So the operation of L plus each time increases the eigenvalue of LZ by plus H cut. Okay. Now what we are expecting? If I keep on applying L plus L plus L plus, so my eigenvalue will be keep on increasing, but we'll show that beta has a maximum limit. Okay, beta is the eigenvalue of LZ. Well, alpha is the eigenvalue of L square. L square is Lx square plus Ly square plus Lz square. So beta cannot be greater than alpha. That we will prove here. So for the moment, I have proved here that L plus square, alpha beta, these all are the eigenstate of Lz. And now I am going to show you that same like L plus L square. Uh, If I operate L square on L plus alpha beta, this is also eigenstate of eigenstate of L square with same eigenvalue. We can prove very easily, because how can we prove here? Because L square commutes with L plus. L square, if I take the L square L plus, this is 0. So I can write easily, I can write this is equal to L plus L square alpha beta. Now alpha operates here, you got alpha L plus alpha beta. So this is the eigenstate of L square, but the difference is here the eigenvalue square L is not changing. That means this operator I called a raising operator, because it is always increases the beta value, that is the eigenvalue of LZ operator by plus H cut. So this is a raising operator, but raising operator does not have effect on the eigenvalue of L square. Now if I do L square L plus square, like I have shown here, alpha beta, then again I'll get a same eigenvalue with L plus square alpha beta. So now we got two facts. One thing I showed you, the operation of LZ increases the eigenvalue of LZ, and then it does not have an effect on L square eigenvalue. Now I will show that beta is bounded. Beta value cannot be increased by a certain limit. So let us prove that one. So say now Now I say I operate say Lx square plus Ly square Ly square. I can write this as the L square minus Lz square because L square is equal to Lx square plus L square plus Lz square. Now let us operate L square minus Lz square on the state alpha beta and see what happens when you operate here. So when I operate here, this will be, so this is equal to this one and now operating here. So L square operates here, you get alpha, and B, this operates is give you beta square, alpha beta. Now alpha minus beta square cannot be a negative because Lx and Ly, they are Hermitian operator, their eigenvalue has to be real. Plus now these are square. So eigenvalue is square. So this cannot be negative. So alpha minus beta square should be positive. Alpha minus beta square should be positive. I could maximum this one. So your alpha is greater than beta square. That means beta value cannot increase by greater than alpha. So there is a higher bound. Okay, so that beta is higher bound. So here, so same way, we can show when my Lz operates on L minus alpha beta on the state, my eigenvalue decreases by h cut, and this is the eigen state with a reduced, lowered eigenvalue. And we similarly we can say apply L square. So L minus is a lowering operator. It decreases the eigenvalue of Lz by minus h cut. This is one thing. And we also similarly, like L square also, we can show that L minus is also eigenstate for L square with the same, with no change of eigenvalue, with no change of eigenvalues. So by knowing these things, now what we can say, how can we understand? So I'm drawing a diagram. So we have a state. Alpha beta. Okay. And when I operate Lz on this alpha beta, I get the eigenvalue beta. Okay. Now same thing if I operate, this is my state alpha beta. And now if I measure L plus Z in this state, my eigenvalue is beta plus h cut. Similarly, if I operate, this is my next state. If I measure Lz here, this will be beta plus 2h cut. And if I keep on moving like this, okay, keep on moving like this, then what will happen? I'll get a state where beta is max. Now you cannot increase by operating the rising operator, the eigenvalue. So in this state, I say that my eigenvalue will be now operate here. The eigenvalue will be now here beta max. Okay. Similarly, if I operate, this is my state alpha beta, and now so this is like a chair. Now this is like a riding ladder. This is like a ladder. And now if I operate here, Lz on this state, I get beta minus h cut. If I operate L minus square alpha beta on this state, if I measure the Lz, it will be beta minus 2h cut. And if I keep on moving, I will have a state, some state called alpha, where beta cannot decrease by further, beta minimum. So beta minimum, here I say my eigenvalue is beta minimum. So this is the picture should be clear how lowering and raising operator change the eigenvalue of Lz, but L square eigenvalue does not change. Okay, that you have to keep in mind. Now I want to find the calculate eigenvalue, so we are just one step away. Now let us say I'm operating L square. So L square on the state alpha beta. Now let's see what happens on the state of beta max. Okay, so we have reached here, and now I'm applying beta max, and I should told you L square by changing the operating L plus L square does not changes its eigenvalue. So this will be equal to alpha beta max. And now L square, how can I write L square? If I use the ladder operators, okay, so I can write Lx minus iota Ly, Lx plus iota Ly. Basically I want to find L minus L plus. Okay, so my L minus L plus will be, because I want to operate here. Now when you reach the maximum state, okay, when you reach the maximum state and if operate L plus on alpha beta max, it further cannot enhance the eigenvalue, so this will become zero. So I want to find this operator now. So let us find this operator. So this will be equal to Lx square plus Ly square and now you have a minus iota. This will be Ly Lx minus Lx Ly minus. Okay, so this will be what, minus. Okay, correct. So now this will, so I will get what? I will get here Lx square plus Ly square and now this is equal to minus iota minus plus iota square plus h cut Lz, and this is, and now I can write L minus L plus is equal to Lx square, and now this is equalent to L square minus Lz square, and then you have a h cut Lz, and now we are going to operate this one L square here. So L square will be basically L minus L plus Lz square minus h cut Lz. Here I will operate here. So this will be L minus L plus Lz square minus h cut Lz operates on alpha beta max. Now see what happens. So this is equal to alpha beta max, and now when I operate here, what will become, say L plus operate on this here, it will be 0 because it cannot further enhance. Lz will give you beta max square, and now here minus or plus, check it. So it should come plus. Okay, here somewhere we have done mistake while writing the this one. Okay, while writing this Lx Ly L minus, while calculating L plus L minus, I want to calculate L minus L plus. This should be Lx minus iota Ly, and then you should have a Lx plus iota Ly. Let me check it again. So this is Lx square, and this is a iota minus plus Ly square, and then you have minus iota Ly Lx. Okay, and then you have a plus iota Lx Ly. So Lx square plus Ly square minus, if iota I take common, then you have a Ly Lx minus Lx Ly, correct. this is opposite. So this will come minus iota, and this is also minus iota h cut Lz. So minus minus plus iota, so minus will come. So here it will plus will come. Okay. So here it will plus will come. So now, so I can say now this is equal to beta max square, and this is operate on this one. You get beta max, the h cut beta max, same state. And if I compare this one, this is equal to alpha. And now similarly, I can show when L square operates on beta minimum, eigenvalue does not change alpha beta minimum. Okay. And now if I write L square in terms of this form, instead of L minus L plus, I write L plus L minus. So this become L plus L minus plus Lz square minus h cut Lz. Now this will be equal to this one, and this will operate on alpha beta minimum. Okay, and this is equal to alpha, same here. And now if you operate here, this one minus will not have any effect, it cannot further reduce. So you will get here beta max is beta minimum square minus, okay, beta minimum square minus h cut beta minimum alpha. Okay. So if I now solve these two equations, okay, you got two solutions, and one solution is beta max, beta minimum is equal to minus beta max. Okay, so we have shown beta is bounded, and then now we're showing beta max is equal to beta minus. Now I say beta max is L. Okay, beta max is L. So here the total, here you will get L h cut. You will get your, the eigen will become L h cut, will show here. So now if I say now so beta value is now here Lz will operate here. You get beta max square. So let us now find the alpha values. Okay, or I say beta is L h cut. Okay, beta is L h cut. So now my alpha will become what? So my alpha will become now beta max square plus h cut beta max. Now this is become L square h cut square plus L h cut square. And if I take uh, L h cut square common, so this become L common, so this become L, and this become plus 1 and h cut square common. So this is the value of eigenvalue of L square operator. Okay. And now what is the, for this, now what is L? Here is a minus H cut. This is minus L h cut. So if I say the difference between L h cut and minus H cut, they are total n steps. They are total n steps. Then I can show that my L is equal to minus L plus n. If I keep on adding h cut here, L h cut minus L cut and n h cut. If I keep on adding the steps, so I can show this is equal to, so this says 2L is equal to n. So L is equal to n by 2. So L can be a number, L can be L can n can be what? N can be 0, 1, 2, 3, so on. So now my alpha values. So this is, so the L values can be what? L values can be, if I put here 0, 1 by 2, 1, 0, 1 by 2, 1, 3 by 2, and then to put here 4 and 2 and so on. This is my values of L. And now beta, we told beta can take value from minus L to plus L. Okay, so I say M. I define beta by now M. I say beta is now M, and it can take value from minus L to plus L. For example, if L is half, then M will be minus half plus half. If L is 1, it will be minus 1, 0, 1 in the step of H cut. Okay, so now I say my beta, the eigenvalue beta, I write it is M H cut. It will be minus L cut to plus H cut. This is the M H cut, where M varies from minus L to plus L. So now finally I write the eigenstate L square alpha beta. Now I replace alpha beta. I replaced by LM. I replaced by LM, and this is equal to L plus 1 H cut square LM, and LZ will be same eigenstate LM, and this is equal to M H cut LM. So this is the conclusion. These are the eigenvalues of, so here alpha M is a basically abstract state. Still we don't know the functional form of the state for this operator. But here you have to keep in mind L is not the eigenvalue. Eigenvalue is L plus H, L plus. Okay, same like harmonic oscillator, N is state. It is not the eigenvalue. If I want to write the eigenvalue, then I have to write this. This is a N plus half H cut omega. That is a messy way of writing. So here L is related by the eigenvalue, but it's not eigenvalue. Here L is the indices. Okay, similarly M is also indices. M is also indices. So now we have find out the how to represent the eigenstate of operator L square and LZ. Okay, and what is their eigenvalue. So I'll stop here. We'll continue with my next video about spherical harmonics, that we'll try to find out the we'll see the how to find out the functional form of this abstract eigenstate, simultaneous eigenstate of L square LZ. So I'll stop here. Thank you.